Welcome back, everybody. I'm Dr. Rhett Smith for ProtonGuru.com. Today we're looking at Lesson 6.5 in the Organic Chemistry 2 Primer 2021. I just want to show you quickly an excerpt from page 126 of the Organic Chemistry 2 Primer 2021. This is not one of the slides that you can find. You can find all the slides at ProtonGuru.com if you want to print them out and fill in the blanks as we go along. This particular picture is not in the slides, though. It's in the primer, which is also available free on the website. And I mentioned in our lecture about the type A, B, C, D reactions this table on page 126 that summarizes the types of reactions. Here's a summary of the type A reactions. They happen when your carbonyl is an aldehyde or ketone. Right? All the carbonyls have very similar structures. They look like this. And this Y group is what differs between aldehyde, ketone, amides, carboxylic acids, etc. The type A reaction, you have a nucleophile that attacks. Now, in some of the types of reactions, this Y group is going to leave as a leaving group. But in the aldehyde and ketone, those are terrible leaving groups. They would be very unstable anions if you were somehow to get them to leave. So that's a very unlikely possibility. So what happens once a nucleophile attacks, if it doesn't just come back off, is that the negative charge on the O will hang around until you add an acid and protonate it. And that is the type A reaction, which is the nucleophilic addition step, followed by the protonation step. The types of nucleophiles that do this, right? We said, okay, aldehydes and ketones do this in terms of carbonyls, but only some nucleophiles do this. They tend to be nucleophiles where you have a carbon with a minus charge on it, like in the organometallics or the cyanide, or a hydride reagent. I guess it could be NaH, which also makes an H minus, or something like a deprotonated alkyne could also do this. But a very reactive nucleophile. So minus charge on carbon or H. And that's really the subject of this particular lesson. Addition of carbon and hydrogen-centered nucleophiles, aldehydes and ketones. So type A reactions. If we have an H minus, which might come from lithium aluminum hydride, let's say, in step 1, of this reaction, we would do nucleophilic addition, which is what's shown, arrow pushing wise here with these two arrows, and we'd have the H added. And this could be an R or an H. That's what this H/R type representation means. That's going to hang around until you do a second step, where I might have just H2O or H3O plus or something like this. And something that provides an H plus will protonate that O. So your final product, of course, will be a neutral organic alcohol. Everything's exactly the same when we use an R minus from a Grignard or an organolithium. Now, remember, we learned a few organometallic reagents that can transfer R groups to things. We learned the Gilman, Grignard, and organolithium. Here I'm telling you that the Grignard and organolithium do this. The Gilman we already talked about doesn't react with carbonyls. The Gilman reagent only replaces halogens with retention of stereochemistry. So important point here, the nucleophilic addition is going to be an R minus that comes from an R lithium, so organolithium, or a Grignard reagent. So we talked about that you can think of these as sources of a carbon-centered nucleophile. Now initially we'll get the deprotonated or negatively charged O. I guess you didn't deprotonate it, there was no proton to take. Instead you just pushed the electron density, electron pair up to the O. But then you need a second step, right? So these reactions will say 1, Grignard reagent, 2, H plus or H3O plus or just H2O, something that has the capacity to provide that proton to protonate your alkoxide group. And that would be our final product in this case. So I wanted to show you a couple authentic examples of what these would look like in real life. The sodium borohydride and the lithium aluminum hydride are two of the hydride sources we talked about. Now we did talk about the sodium borohydride being the least reactive of the hydride sources we talked about, but it is reactive enough to react with aldehydes and ketones. So when we see this reagent, hopefully you will think that means that my nucleophile is this, hydride. Same thing here. And then you have to go through the thought process of saying, okay, if I have an aldehyde or ketone, what I do is I do the nucleophilic addition in either case. So they both would give me the same initial compound with the minus charge on the O. And step 2, in both cases, whether we say it's going to be water or an alcohol or H3O+, the purpose of that second step is to supply the proton necessary to protonate the negatively charged O. So we get these alcohols in this case, and I've highlighted the added nucleophile by making it a red color here. A couple more authentic examples of what you would see if we were adding an R- type nucleophile. You see the Grignard reagent. I hope that you would think that is a source of nucleophilic alkyl group, or whatever that group is. Same for organolithium. Nucleophilic addition in either case. And whether that Y is an R or an H, it will work for an aldehyde or a ketone. And in box A and B, we get the same sort of initial products we had for the hydrides, with the exception being that instead of an H being added from the hydride nucleophile, we have the alkyl nucleophiles added. And we'll get species that look like this. The purpose of the second step, again, being to protonate the negatively charged oxygen. So we have a variety of ways here to make alcohol. A couple of things I'd like to point out with these addition reactions, whether we have this type of reaction where we add an H or this type of reaction where we add an R. If we were to make a chiral center here, say we had two different R groups and an H, we would have to make a racemic mixture. So we're not changing any of the rules that we learned before if we start with an achiral starting material. Right? None of this stuff is chiral in the reactants and reagents. If we were to make a chiral center, we'd have to have a mixture of configurations 50-50 at that site. That's a racemic mixture. Now, a related reaction would be the reaction of a ketone or an aldehyde. Say we have an aldehyde here with a cyanide salt. Now, I hope you'll remember from our discussion of SN1, SN2, UNE2, that the ionic compound will dissociate into cation and anion. Here we're interested in the anion as a nucleophile. In this way you get a CN. We're going to learn some reactions that these can do later, so this could be an important step in some multi-step syntheses. So the first step was NaCN to access that point. The second step is going to be some type of acid. The point of that will be again to protonate this. And here you've generated a compound that's known as a cyanohydrin. Interesting reaction for now. It follows the same sort of type A pathway that these other reactions do. But we'll see that the cyanohydrin formation is an important step in some biologically relevant reactions a little later in the course, so it's worth keeping in mind.